All right. Good morning, everybody. Welcome back. So this is going to be our final week of classes. And so it's a short week. We will have lectures on Monday and Wednesday. And then for Friday, we will have our final in-class assignment. So let's start this week with some quick announcements here. You have online homework for chapter number 9 due on Thursday, and for chapter number 10 due on Friday. And then we will have our final in-class assignment this Friday. For the final exam, I already posted a practice worksheet. And then on Wednesday, at the end of the lecture, I will give a little more details about the format of the final exam. And if I'm not wrong, the date for the exam is next Wednesday, if I'm not wrong. So I will double check that and we will discuss on Wednesday all the details. Okay, so let's do here a quick recap about molecular geometry, the things that we discussed last Friday. So for the molecular geometry, I will look at the molecular geometry of the central atom. So therefore, all the rules that I showed you apply to the central atom. The first step is to determine the electron pair geometry using the steric number, and that will take into account all the bonding and non-bonding pairs around the central atom. And from the electron pair geometry, we are going to extract the molecular geometry. For the molecular geometry, we are going to take the electron pair geometry and fill up the spots that are available for the atoms. You can always follow this table here that will give you all the situations that are possible to happen. On the vertical axis, we have the steric number. And then on top of each column, the number of lone pairs located at the central atom, okay? So 0 lone pairs, you have all these possible geometries, and then 1, 2, 3, or 4 lone pairs, then you start to have different geometries. This is also a very nice table because it has here the angles between each bonds. Okay, so for example, a trigonal planar geometry, the angle between each bond here is 120 degrees. Okay. And we talked about the molecular geometry for CO2, nitrate as well, and PCl5. So for today, I would like to talk about the molecular geometry for water, and I would also like to discuss the molecular geometry for ammonia. Okay, so let's start with water. So let me switch really quick here to my other screen. Okay, so we will do water and ammonia. Ammonia is NH3. So let's start here with water. Always the first step in determining the molecular geometry is to draw the correct Lewis structure. So I'm going to pass through that uh, slightly fast. So water, we know that oxygen is the central atom, single bonded to two hydrogens, and then you have uh, two lone pairs or non-bonding pairs located at the oxygen atom. First step here is to determine the steric number, and with that, we are going to determine the electron pair geometry. Okay. So the steric number, you are going to consider bonding and non-bonding pairs looking only at the central atom. Okay. So this is the atom that we are going to look at. So we have two single bonds. Each one contributes with a unit to the steric number, and two lone pairs, each one contributes with a unit to the steric number. So therefore, our steric number is 4. Steric number for the most stable geometry to arrange 4 groups around a central atom is tetrahedral. And that's going to be the electron pair geometry. Here. From the electron pair geometry, we are going to figure out the molecular geometry. I have the table here. Okay, so that's the electron pair geometry. So we have here a tetrahedral geometry. However, for the water, we just have two positions that are occupied by atoms and two positions that are not occupied by any sort of atoms. If you go back to the big table, for steric number equals to 4, with two lone pairs, what we are going to have is a bent geometry or angular shaped or V-shaped geometry. So therefore, the molecular geometry for the water molecule, let me use here the same name that's being used in the table, and there it says angular. Okay, so that's how you move from Lewis structure, electron pair geometry, and molecular geometry. The electron pair geometry is going to give you the geometry of everything around the central atom, and the molecular geometry is going to look at which atoms are bonded to the central atom. So we are going to hide here the non-bonding pairs, and that's the molecular geometry for water. Okay. Okay, so now let's take a look at uh, the ammonia molecule and H3. Starting always with the Lewis structure. So when you are drawing the Lewis structure, it doesn't matter how you distribute the atoms in the space. So we are just going to do a random arrangement here. We know from Clark's rule that we only have single bonds and there is a lone pair located at the nitrogen atom. Okay, so first step in the determination of the molecular geometry is to determine the steric number. Again, we are only looking at the central atom. So let's take a look at the nitrogen. 3 single bonds, each one contributes with an unit. And one lone pair that contributes with a unit. Daily, just give me a second and I will answer your question. So therefore, again, we have here steric number, oops, equals to 4. Again, steric number equals to 4. We have the same situation as the oxygen in the water molecule. The best way to arrange 4 groups around the central atom is to distribute them as a tetrahedral geometry. And that's going to be the electron pair geometry. And in this case, for the electron pair geometry, we are looking at bonding and non-bonding groups. For the molecular geometry, we are just going to look at the bonding pairs connected to the nitrogen. So let's go back to the table. So we have here steric number 4 and just one lone pair. And in this situation, the molecular geometry is going to be, let's see here what the table calls, trigonal pyramid. So that means only 3 positions from the 4 available have atoms, and we are going to ignore the lone pair for this geometry. So that's what we are going to have for the ammonia molecule. See that one bond is coming out of the plane, the other bond is moving towards the plane, and we can draw here another bond on the plane. So to make a nice drawing for the ammonia molecule, We are going to put here nitrogen. One bond is going to be on the plane, another bond coming out of the plane, and we are going to indicate that by this bold bond, and a third bond going towards the plane. Then, oops, we can symbolize that by the dashed bond here. Okay, so this indicates that we have this 3D shaped molecule. Okay, so now, Daily, I can answer your question. Angular geometry or bent or V-shaped, they mean the same thing, okay? So in all these cases, we have a molecule that looks like a V, and you can name this geometry as angular, bent, or V-shaped. It's going to be to mean the same thing. Just to make easier, just use whatever the table tells you the name is, then it's more consistent. Okay, very good. Uh, let's tackle here a final example, and then we are going to move on to polarity of molecules. So let's give you a couple minutes, try to set up the Lewis structure of the compound, and then electron pair geometry, and then let's draw the molecular geometry. Okay, so SF4. First step, Lewis structure for SF4. So we can draw this step without worrying about the arrangement in the space. So let's randomly draw 4 single bonds. Then we are going to fill the other end of the bonds with fluorine atoms and distribute the remaining electrons to fill up the octets of all the fluorine atoms. And then, according to Clark's rule, this is an example of octet expansion for the central atom. So we are going to dump the remaining electron pairs on the central atom. Therefore, here we have sulfur with 10 electrons in its valence shell, sorry. Okay, so after that, so see here, drawing the correct Lewis structure is a crucial step to get on the right path to determine the electron geometry. So if you feel like you are not good on drawing Lewis structure, I strongly recommend you to go back and review the last chapter. Okay, so now we are going to look at the central atom. And first step, determine the steric number. We have here 4 single bonds. Each one contributes with 1 unit to the steric number. And we also have 1 non-bonding pair, and that's going to add 1 more unit to the steric number. So therefore, here we get a steric number equals to 5. When you have a steric number equals to 5, the electron pair geometry is going to be a trigonal bipyramidal. Okay, so let's see here what we are going to have is something like that. Okay, so we have a triangle on the plane. All the sides are the same, and then 1 bond up and 1 bond down. That's why it's a trigonal 1-2 bipyramid. Okay, so bipyramid always means 1 bond up and 1 bond down. It's like you have 2 pyramids, 1 up and another 1 down. Okay, very good. Now that we know the electron pair geometry, from that we are going to extract the molecular geometry. All right, for the molecular geometry, we are going to look only at the central atom and the atoms bonded to the central atom. And we are going to derive the molecular geometry from the electron pair geometry. So let's go back to the table. So steric number 5 and 1 lone pair located at the central atom. So that's the only one that's missing the name. So for this case, the molecular geometry is going to be called seesaw. So we are going to have, from the 5 available positions, 1, 2, 3, and 4 filled up. So like that. And then we are going to ignore, for the molecular geometry, this one that's not bonded to anything. So what we are going to have is something like that, okay? A seesaw shape. To get a nice drawing of this molecule, we are going to draw here the central atom, these 2 bonds on the same plane, and then 1 bond pointing out of the paper and the other one towards the paper. So let's make a nice drawing here. Sulfur molecule, 2 bonds on the plane. Okay, so these 2 bonds here. Then to symbolize this bond coming out of the plane, we are going to use that bold drawing. And then the final bond that's going up towards the plane, we are going to use that dashed notation. Okay. And again, this is the seesaw geometry.
Hey, Professor.
Yes.
Why wouldn't you just use the term the trigonal bipyramid instead of seesaw? Where did the word seesaw come from?
Okay. So let's see here. When you have the the trigonal bipyramidal geometry, that means you have 5 electron groups around the central atom, and that's the electron pair geometry. However, when you are looking at the molecular geometry, you are not going to count the non-bonding pair because it's not bonded to any atom. So we remove the non-bonding pair from the equation. And then that's what you are looking at for the molecular geometry. Does that answer your question?
Kind of. I'm just unsure where you got the term seesaw from.
Seesaw is when you have 1 central atom and 4 bonded atoms and a lone pair here at this position.
Okay, because it's not on any of the it's not on the chart that you gave us. So
Yes,
just
yes,
where that came from.
yes. So that's the only name that's missing in the chart.
Okay.
Okay.
Thank you.
Mm-hmm. Okay. Now, the last topic for today will be talking about polarity. So we know how to determine the polarity of chemical bonds. And for that, we are going to look at a specific chemical bonding and the electronegativity difference between the atoms involved in this bond. And then from that, we are going to look at the polarity of the whole molecule. When we are looking at the whole molecule, we are going to consider each chemical bond as an individual vector. And for the overall polarity of the molecule, we are going to add up the individual vectors. Remember that we have a order of electronegativity. So fluorine, the highest one, followed by oxygen, nitrogen, chlorine, bromine, iodine, sulfur. And then here we are going to consider carbon, the same as phosphorus, the same as hydrogen. Okay, from right to left, I'm increasing the electronegativity. Remember that electronegativity is the ability to pull electrons from a chemical bond closer to the atom. So therefore, fluorine will always win the battle. Carbon, phosphorus, and hydrogen, they will always lose the battle. And we are going to consider that the three last elements, they have the same electronegativity. So determining the polarity of the molecule is extremely sensitive to the molecular geometry of the molecule. Let's start here with carbon dioxide. We have carbon bonded to two oxygen atoms by double bonds. And this arrangement is a linear arrangement. What I'm going to do to determine the molecular geometry now it's to draw the vectors corresponding to the polarity of each chemical bond. So let's first analyze the left side of the compound. So we have here carbon and oxygen. So carbon is right here. Oxygen is basically on the opposite of the scale. Therefore, oxygen wins the battle. And I'm going to represent the vector for this chemical bond pointing from the less to the more electronegative atom. Okay. So that means there is a shift of the electron cloud towards the oxygen to the left. And then we are going to do the same thing for the oxygen to the right side of the compound. So it's the same case. Oxygen wins the battle. And to represent that, I'm going to draw a vector here that's pointing from carbon towards the oxygen, always from the less to the more electronegative atom. Okay, so with that, we determine the polarity of each chemical bond. The overall polarity is going to be the sum of all the individual vectors. Okay, and the intensity of the vector is also proportional to the electronegativity difference. So if we have a linear geometry and one atom is pulling to the left side and the other atom is pulling to the right side with the same intensity, the resulting vector for this geometry is going to be 0. Okay, so resulting vector, I'm going to represent that by mu r is going to be 0. If the resulting vector is 0, that means we have a non-polar molecule. So look first at the individual chemical bonds, see if there is a pull to one of the sides, draw the vector that represents the direction of the pull, and then for determining the polarity of the whole molecule, we are going to add up all the vectors, okay? So you have to remember how to add vectors. For CO2, linear molecule, the pull to the left is the same intensity as the pull to the right. That will cancel the vectors, resulting in a non-polar molecule. Now let's take a look at sulfur dioxide. Apparently, they should be similar, one central atom bonded to two oxygens. However, because of sulfur has a non-bonding pair, that will affect the molecular geometry for SO2 compared with CO2. So for SO2, now instead of a linear molecule, we are going to have a bent or angular or V-shaped molecule. And now let's take a look and see if that change in geometry will affect the polarity of the molecule. Again, here, look at the individual chemical bonds. So let's look first at sulfur and oxygen to the left side. See if there is an electronegativity difference between the atoms. So in this case, we have sulfur different from oxygen. And we know from the order of the electronegativity that oxygen is the more electronegativity. Therefore, it will pull the electrons in the chemical bond close to itself. So we are going to represent that by a vector pointing from the sulfur towards the oxygen atom. And then the same thing for the oxygen atom to the right side of the drawing. Is the same situation. So we are going to have a pull from the sulfur towards the oxygen atom. So we are going to represent that by a vector that starts on the sulfur and points to the oxygen. Okay, so that was the determination of the polarity of each chemical bond in the compound. So now let's take a look at the overall polarity of the compound. So I'm going to represent the central atom by a point. And what I'm going to do is to draw the vectors here that I already figured out. So the blue pointing towards the oxygen, and then the red also point towards the other oxygen. Okay, so at this point, we need to calculate the resulting vector that is resulting from the addition of the two vectors to determine if the molecule is polar or not. So when we have two vectors pointing down, there are two ways to determine the resulting vector. First one is to project the red vector at the top of the blue one, at the end of the blue one, and then the same thing with the blue at the end of the red vector, and then the resulting will be from the center towards the crossing from the projection of the two vectors. Another way to get the resulting vector is to redraw the blue, and where the blue vector ends, we are going to draw the red vector. Okay, so the head of the blue vector will connect to the end of the red vector, and the resulting vector will start at the beginning of the blue, pointing towards the end of the red vector. So those are two ways to do the same thing. What matters here is that now we have a resulting vector, mu r, that is different from zero, okay? So two things pulling down with an angle will result in a down pull. So therefore, when the resulting vector is zero, that means we have a polar molecule. See that a slight difference in the molecular geometry comparing CO2 and SO2 results in a big change of the polarity of the molecule. CO2 is nonpolar, SO2 is polar. The only difference between them is a non-bonding pair located at the sulfur atom, and that changes everything. What's the importance of determining the polarity of molecules? Polarity is strongly related with solubility. Polar molecules dissolves polar molecules, while non-polar molecules solves non-polar molecules. Okay, similar dissolves similar. It's very unlikely that a polar molecule will dissolve a non-polar molecule. And that's why CO2 is less soluble in water than SO2. Water is polar, CO2 is nonpolar, that results in low water solubility for CO2, while SO2 is polar, and that will render a higher solubility in water for sulfur dioxide. Okay, so let me go back to the PowerPoint. Okay, very good. Okay, so let's answer a couple more questions that were asked at the beginning of the chapter. Why sugar has a sweet taste, and can we create molecules that trigger the same sensation? Sugar has the right size and charge distribution to interact with taste receptors in our tongues, okay? So the sugar molecule has the right shape to interact with those receptors. The interaction causes stimulation of electric pulses that will trigger the sweet sensation. When you are creating an artificial sweetener, you are going to try to design a molecule that has the same shape and charge distribution as natural sugar to also interact with the taste receptors. And sometimes the design is so good that the interaction is so strong, and that seems like the sweetener is sweeter than sugar, okay? So this sensation means that the artificial sweetener is interacting in a very strong way with the receptors. And the chemical process behind the vision. So in our eyes, we have this compound called retinol. So we have here a double bond. And when there is light, we switch the configuration of this double bond. Instead, the bonds pointing down, we have one pointing down and another up. So this switch will generate electric pulses, and your brain will reconstitute the image according to the number of electric signals. Okay, so with that, that's where I stop the lecture for today. And on Wednesday, we will tackle intermolecular interactions. And then I will see you tomorrow for the discussion section. I hope you have a good week. Bye-bye.